Okay, welcome back, students. So I wanted to address two things that I failed to mention last time, just so that we're all on the same page with them, sort of moving forward. So the first is the textbook. The textbook has a picture on the front of it that looks something like this. Yours may not look exactly like this because this happens to be the instructor's edition, but ultimately this is sort of what the cover looks like. It looks like there's sort of like a bridge of some sort, reflected in water, whatever it may be. Ultimately, pre-calculus mathematics for calculus. This book will be valuable to your sort of to your skills development throughout the course of the year. It provides a resource for you. I do believe that the resources that we'll work through together will be at least as valuable. Yeah, the textbook is there, and the ISBN number is listed on the syllabus in the event that you haven't got your hands on it yet. Remember that whenever you get your hands on the textbook, or however you get your hands on the resource materials for this class, remember that in addition to the textbook, you're going to need a WebAssign access code. All of our homework goes through the WebAssign system. The WebAssign system corresponds exactly to the textbook. So every section of the book that we cover, there's going to be problems from WebAssign that are exactly associated with those sections. So WebAssign written by the textbook manufacturer. But the WebAssign is 100% essential. Having the textbook alone does not get you access to WebAssign. You're going to need access to WebAssign to get the book. Of course, if you get the textbook in online form, that's totally fine. That can work for you as a resource without any issue. One more thing that I wanted to mention that was not mentioned last time, but is worth mentioning, is calculators. This course requires a calculator technically because there will be times within the course that homework problems specifically will demand a calculator in order to solve the problems. As I say that, no test that we have in this course, whether it be the 4-chapter test or the final exam, will allow you to use a calculator. When you go into each test, when you go into the final, I mentioned this sort of implicitly last time, but it is going to be you, a pencil, and a piece of paper. No calculator. Now, that may be super unsettling. Just know that no matter how much your knowledge of math crutches on a calculator currently, as we go through this semester, we will crutch on a calculator as minimally as possible. And as I say that, what that really is ultimately going to entail in practice is that as we go through the entire semester, there's going to be like one lecture all semester long where we're going to use a calculator. And other than that, we're going to do everything that we do here in class, just like you'll do on the test without a calculator. So I don't want our knowledge to crutch on a calculator when our knowledge is not going to be able to be crutched on a calculator when we're taking the test. 55% of your grade for in-class tests, 30% for the final. So we're going to work throughout the course of this entire semester to develop an understanding of the material that is free from the calculator. So in some sense, that's going to be liberating, because even if your past math understanding has been based with the calculator as a crutch, you are now going to be freed from having to use those mathematical crutches as you go through the mathematical content of this course. So textbook, you have the ISBN number on the syllabus. Make sure you get a WebAssign code if you have not already. There will be homework assigned from today and tomorrow's class, which is going to, well, would normally be due on Sunday, but it's technically going to be due next Sunday as a result of giving you time to get a WebAssign access code. But know that if you don't have a WebAssign access code, get that as quickly as possible. And calculators, we're not going to need them to solve almost everything that happens in this class. And the things where we are going to use a calculator are going to be on problems that can't even be on the test. So, yeah, we're going to work all semester long to free ourselves from that. So, with that in mind, let us now sort of venture off into the pure mathematical content of the course. And let me be very clear here. Like, we are going to start with fundamentals. We are going to start with basics. But these fundamentals and these basics, as in some sense, like simple as they may seem on the surface, are going to be skills that we are going to call upon regularly throughout the course of the semester. They're going to be skills that are going to be necessary to have fully grasped in order to have success in this course. So while what we go through here may seem simple, these are the basic building blocks upon which the entire course is developed. So let's start in section 1.1, which discusses the real numbers. So every day in class as we go over a particular section so that what I do corresponds to what is in the textbook, I'm using this notation, chapter 1, section 1, 1.1, and my headings may not always agree with exactly what is in the book, but they're going to be closely related enough. So, what are real numbers? I mean, we talk about, I just drew the word real numbers up here, but what does it mean for something to be a real number? Well, as we sort of mathematically describe it, real numbers are any number on a number line. So I'm sure you've seen before a number line, often centered around 0, going off in the positive direction or going off in the negative direction as far as you want in the positive or negative direction. Because while I drew this number line only going up to 2 per se or down to -2, this number line with this arrow extends off to the right forever. So you would encounter positive 3, positive 4, positive 5, and so on and so forth. Moreover, just because I have written a -2, a -1, a 0, a 1, and a 2, don't think that the only numbers on the number line are the whole numbers. Because you know that you could pick a point halfway between 0 and 1 and you'd be at a half. You could pick a point a quarter of the way between 0 and 1 and you'd be at a quarter. You could pick a point anywhere between 0 and 1 and you would be somewhere. I mean, hell, go out to the right a little bit further, you'd run into like 3.14159 ... out forever. You could run into pi on the number line. Pi is just a number, in some sense, between 3 and 4, closer to 3 than 4. So, pi is a real number. Why? Because it's on the number line. A quarter is a real number. Why? Because it's on the number line. A half is a real number. Why? Because it's on the number line. 2 is a real number. Why? Because it's on the number line. Any number that's on the number line is a real number. Why? Because it's on the number line. Now, when we work with real numbers, when we work with any number off the number line, we could start operating with those numbers. Because rather than just dealing with a single number, we could see how two numbers, for example, interact. So we could start introducing addition, subtraction, multiplication, or division. Now I want to make a note whenever we start operating on numbers. Because you can take any two real numbers, any two numbers off the number line, and you can add any two numbers. So let's just note here, you can add any two numbers. Well, specifically, any two real numbers off the number line. Take the two numbers, add them together. 2 plus 3, 5. 2 plus minus 1, 1. Add any two numbers, you can do that. For that matter, you can subtract any two real numbers. Hell, you can multiply any two real numbers. Take any two real numbers and multiply them together. 2 times 3, 6. 2 times 10, 20. 4 times 15, 60. Pi times 20. Whatever it comes out to be. 60 point, whatever, 62.8, I don't know, whatever it is. But, here's the most important thing to note. You can divide any two real numbers, except you can't divide by 0. Any two numbers off the number line can be added. Any two numbers off the number line can be subtracted. Any two numbers off the number line can be multiplied. But any two numbers off the number line can't be divided. There is one exception to addition, subtraction, multiplication, and division, and it is division by 0. Which, just to sort of see that in full scale, let me write it over here, sort of in a bubble of thought. Why this can't be, just think. Say x divided by 0 was equal to, well let's say this, say 6 divided by 0 was equal to something. right? If 6 divided by 0 is equal to something, what would that something have to be? Well, doing what you know you can do with a statement of equality, you can do anything to both sides. So long as you do the same thing to both sides, you'll get something equal back in return. Well, what if you want to get that 0 out of the denominator? You could multiply both sides by 0, and you'd get 6 equals x times 0. So if division by 0 was something, the something it would have to be would have to multiply by 0 to give you 6. And what in the world could multiply by 0 to give you 6? Well, that's sort of preposterous, right? So when you're dealing with real numbers, you can't divide by 0. Now, let me be very clear about this as well. If it was 0 divided by 6, totally different story, right? Multiply both sides by 6. The number that multiplies by 6 to be 0 is 0. So you can take 0 and divide it by anything that's not 0, but you can't take anything which is not 0 and divide it by 0 and make anything that makes sense. Now, you might wonder, what if you put 0 over 0? That's a more interesting question than we really have the ability to answer here. And 0 over 0 is actually something that shows up quite frequently in calculus. But for our purposes now, addition, subtraction, multiplication always works no matter what two numbers you're working with. Division always works unless you're dividing by 0. Anything that is divided by 0, we say is not defined, because it's really not clear exactly what 6 divided by 0 is. So in the case where you are dividing by 0, we say that thing is mathematically undefined. Okay, so we're just going to proceed here. I mentioned at the beginning, this is just going to seem kind of basic, but we're just going to be rolling through specific properties that are going to show up, specific operations, specific situations. And let's just take these. It may seem like a smattering of ideas at this point, but let's just take these things one at a time, knock them out, get them under our belt, familiarize ourselves with these, re-familiarize ourselves with these things, so that we can get ourselves at a level of understanding to build up from. So first, distributive property. The distributive property essentially answers the question, is how do addition and multiplication interact? So what if you had something like this? What if you had like 2 times 5 plus 3? Note, you know this already, but just note for your mind's eye as we go through the semester, anytime you have two things written next to each other with nothing in between, it means to multiply. So a 2 written next to the parenthesis with nothing in between technically means multiplication. And here we're taking 2 times 5 plus 3. Now you know what you standardly do whenever you see something in parentheses. You like to go inside the parentheses and simplify what's in the parentheses first. Well, if you did that, you get 2 times 8. And if you multiply that out, of course, 16. Now, is that the only way to compute this result? To think of it as 2 times 8. Well, what is 5 plus 3? That's like 5 of something plus 3 of something. Of course, that's where you get the 8 of something, but if you take that 5 of something and that 3 of something and you multiply each by 2, you could utilize what we call the distributive property, which is to say, if you took the 2 and distributed it to each of the terms that are being added, so instead of saying twice 8, you have twice 5 and twice 3, that will in fact give you the same result. 10 plus 6 is 16. So what's interesting is, while you can simplify what's in the parentheses straight away and multiply, you also could not simplify what's in the parentheses and get the same result by distributing the 2 via multiplication to the two numbers being added. Now at this point you say, why would you do such a thing? Because it's almost simpler to do the 2 times 8 than it is the 2 times 5 plus the 2 times 3. Well, what if you had an example that was like 2 times x plus 3? Because you see here, the x and the 3 cannot be combined in any way. They're not like terms. 3 is a number and x is an x. So since you can't add 3 and x because we don't know what x is, if we knew what x was, we wouldn't use x to begin with. We can't add these things inside, so the only thing we could possibly do to change the expression of this But to say the same thing in return, just in different words, would be to undergo the distributive property. So 2 things written next to each other with nothing in between means to multiply. Take the 2, distribute it to the 2 terms, and you'll get 2x plus 2 times 3. Well, of course, 2 times 3, well, I didn't write that out, right? That comes out to be 6. Note the 2x here, 2 times x, how would you write that? You can write the 2 and the x adjacent with nothing in between. 2 things written next to each other with nothing in between implies multiplication. Okay, so we see how multiplication and addition could interact. By the way, let me just make a note. If this plus in here happened to be a minus, x minus 3, well then the 3 is not a 3 but a negative 3, and that would make the 6 not a 6 but a minus 6. So we carry the negative through if we happen to have a minus sign between the 2 numbers. Let's sort of raise this one little bit of problem-solving skill, and what if we had something like the following? Y plus 2 times x plus 3. Now this may look like a something that's unrelated to the distributive property, but I claim it is completely related to the distributive property, because what we have are we have 2 things being multiplied. And just like we did above, where you can take the 2 and distribute it to the x and distribute it to the 3, we're going to do the same thing here. Although, the thing that we're going to be distributing here is not going to be a single term, but a term that is itself a combination of terms. So what are we going to do? We're going to take this x plus 3 and distribute it to the y and distribute it to the 2. So take the x plus 3 and distribute it to the y, you're going to get y times x plus 3. Put a plus sign in between, because now when we distribute to the 2, there's a plus sign in front of the 2. So since the plus sign is in front of the 2, separating the y and the 2, we're going to put a plus sign in front of the 2, separating the y and the 2, and that 2 is going to have x plus 3 distributed to it. X plus 3 distributed to the y, x plus 3 distributed to the 2, separated with a plus sign because the y and the 2 are separated with a plus sign. And now, how can we work this out? Well, you see now, we have just a single number distributed to the 2 numbers, and now we can simplify this fully. Yx plus 3y plus 2x plus 6. Note, I wrote that as 3y instead of y3. It is conventional, whenever you're writing a number and a letter, to put the number out in front. So I wrote that as 3y instead of y3 to imply, just to write it the standard way, that well, of course the 3 is written next to the y with nothing in between, which means a multiplication, but ultimately, the 3y is there just to be written the standard way, numbers before letters. By the way, you may have seen in your past, you may have remembered in your mathematical past how to multiply these things, and you may have referred to it as the FOIL method. That's exactly what we get as a result here. The first 2 numbers, the yx, the outer 2 numbers, the 3y, the inner 2 numbers, the 2x, and the last numbers, the 6. The point of going through this exercise of taking the one term and distributing it to the other term is to show you how the distributive property is at play in a problem such as this. Okay. To be clear, we're going to use the distributive property a lot, and having a firm grasp of this, essential to having success in this course moving forward. Next. Subtracting a collection of terms. What if you're not just subtracting one thing, but you're subtracting a collection of things? So what if you had something like this? Well, of course, 10 minus 2 is 8. No sweat, right? But what if you didn't have 10 minus 2? You had 10 minus 2 plus 3. Now you can see what this would be equal to if you followed your nose with parentheses and said, okay, let's try to simplify what's inside the parentheses first. This is going to be 10 minus 5. 10 minus 5 is 5. No sweat. But another way to think about this is that 10 has subtracted from it a collection of things. So 10 has subtracted from it a 2, and 10 has subtracted from it a minus 3. So, if we're going to subtract this collection of things, we have to make sure we subtract everything that is in that collection. So, 10 minus 2 minus 3 would be the value of the subtraction. Subtract the 2, subtract the 3. And what ends up as a result? 10 minus 2 minus 3, it's the same 5 as before. Now again, as you look at this, you might say, why would we do this problem in such a way? Because it's simpler to just do it 10 minus 5. Well, again, what if you were in a situation where you didn't just have numbers inside your parenthesis? Well, now you can't add x and 3 because x and 3 aren't like terms. 3 is a number and x is an x. There's no way to know what 3 plus x is because we don't know what x is, else we'd use something other than x to describe it. So the only way we can say it is 3 plus x or x plus 3. But now if 10 is being subtracted from, if this is being subtracted from 10, how are we going to express that? Well, using this property that we just sort of observed, whenever we're subtracting a collection of things, make sure we subtract everything in that collection. Well, we've got to subtract the x, and we've got to subtract the 3. Which now you can see how that comes together, because we've got a 10 and a minus 3, which whenever we combine those, since numbers can be combined with numbers to simplify, we're going to get a 7, and the remaining thing being a minus x. So the 10 and the minus 3, a positive 10 and a minus 3 combine to be positive 7, and the minus x is the remaining stray part of the expression. But ultimately, 10 minus x plus 3 is like 7 minus x, because the 3 is being subtracted as well as the x. Taking it one step further, just to emphasize the point fully, what if we had something like this? 5 minus x minus y plus z. So here, we are subtracting from 5 this entire collection of things. And just as before, if you're subtracting an entire collection of things, you have to subtract everything in that collection. Well, what things are in that collection? Well, there's an x, there's a minus y, and there's a z. Subtracting the x is a minus x. Subtracting the minus y, even as you hear that, subtracting a minus y, that's subtracting a negative, that's going to be plus y. Since we're subtracting a negative, that's going to come out as a positive. Finally, we have to subtract the positive z, so subtracting the z is simply doing that. We can't combine any of these terms here because x, y, and z are all unknowns, all different unknowns, and different from a number, 5. But the long story short is, since x minus y and z were all being subtracted from 5, we have to subtract the x, subtract the minus y, and subtract the z. Next thought or idea, adding fractions. This is an absolutely essential skill, and my gosh, without a calculator especially, right? We've got to learn how to do this on our own without that crutch. So how can we do that? Because man, we're going to add fractions fairly regularly as we go through the semester. This needs to become something that's practically second nature. If it's not yet, we're going to have the semester to help prepare ourselves to make it second nature. But ultimately, we've got to get this under our belt. So adding fractions. Let's think of an example. So let's do 3/10 plus 4/15. Now, we're trying to add these things together. Now you know how to add two things together. Like if you've got a clump of 10 things minus a clump of 2 things, you're going to have 8 things remaining. Here though, it's not as simple in some sense because we're dealing only with fractional portions of numbers instead of whole numbers. But we can still work with this. So how can we work with this then? Well, think about what 3/10 is. 3/10 is like a pizza cut into 10 pieces where we have 3 of those slices. let's just say 3 slices of a slice from a pizza that's been cut into 10 pieces. What's 4/15? Well, here, this pizza, rather than being cut into 10 pieces, has been cut into 15. So this piece, maybe it's hard to tell in the picture here, but I tried to draw this piece thinner than the other piece. Because if this pizza has 10 pieces, this pizza over here has 15. More pieces means smaller pieces, like each piece is smaller in size. Now, we have 4 pieces of this size, and on some level you might think, well, 4 is more than 3, I'd rather have these 4 pieces. Well, that's not exactly clear, right? Because these pieces are smaller. Would you rather have 4 smaller pieces or 3 bigger pieces? And really, which of these number of slices is more pizza is not even the question here. What we're trying to do is add these 3 pieces to those 4 pieces. Well, we can't just say there's 7 pieces of pizza, because depending on how you cut your pizza, 7 pieces could mean so many things. What if you don't even cut your pizza into pieces, and they're just whole pizzas? Well, 7 pieces is 7 pizzas. And in this case, 7 pieces is some amount of a pizza. How much of a pizza is it? Well, in order to make sense of the pieces, we need to consider the pieces to be of the same size. So how can we do that? Well, we can do that in the following way. We just need each of these fractions to be in a different form to where the number of pieces in each pie are identical. Now, how could you do that? Well, you see, you could take this pizza with 10 pieces, and if you wanted to, you could chop each piece into 2 pieces. And now your pizza would have 20 pieces. One possibility is to cut each piece into 2 pieces and have 20 pieces. What if you cut each piece into 3 pieces? Now you'd have 30 pieces. What if you cut each piece into 4 pieces? You'd have 40 pieces. Cut each piece into 5, 50 pieces, and so on. So these are the possible piece configurations based on how many pieces you cut each slice into. Cut each slice into 2 pieces, 20 pieces in your pie. Cut each slice to 3 pieces, 30 pieces in your pie, so on and so forth. What about with the 15-piece pie? Well, if we wanted more pieces of pie so that we have like different size pieces to possibly be in harmony with the other size pieces, we could cut each piece into 2 pieces and give ourselves 30 pieces in our pie. We could cut each piece into 3 pieces, and that would give us 45 pieces in our pie. Cut each piece into 4 pieces, 60 pieces in the pie. Cut each piece of this 15-piece pie into 5 pieces, and you'd have 75 pieces in your pie, and so on. Now, here's the thing to think about. Well, pie A could have pieces of 10, 20, 30, 40, or 50, depending on how many pieces we cut each individual slice, or each original slice into. Pie B could have 15, 30, 45, 60, 75. Now, how many pieces are we going to choose? We're going to choose a number of pieces that's equal. Note, the simplest way to do that is with 30 pieces. So, what we need to do to get 30 pieces is we need to cut each of these pieces into 3 and cut each of these pieces into 2. That's going to give us 30 pieces per pie. So, when we cut that first pizza from 10 slices to 30 slices, when we took the number of pieces and multiplied by 3, that took the number of pieces that we had and multiplied it by 3. 9/30. In the other pizza, to get 30 slices, we took every slice and we cut it into 2, but that then took every slice that we had in consideration and cut it into 2, now giving us 8 slices. But here's the thing. Once we take that first pizza, take each slice it into thirds, and get 30 pieces per pie, and take this second pizza and cut each of its pieces into 2s to get 30 pieces. Each pizza is cut into 30 equal pieces. So now, the pieces that we're working with, the 9 pieces here and the 8 pieces there, are now indeed pieces of the same size. So it's not just 7 slices as it was before, where those slices are of different size. Now it's 17 slices, and they're of exactly the same size. Because we have 9 pieces from the original pie, 8 pieces from the second pie, and these are both from pies that had been cut into 30 pieces. So we have 17 pieces from a pie having been cut into 30. Long story short, how can you phrase what we just discussed in sort of concise language? You could say this. When adding fractions, you need a common denominator. The denominator is the number in the bottom half of the fraction. When you're adding fractions, you need the number in the denominator to be common. Why? Because when the number in the denominator is common, your pizzas are of the same size. The pieces of pizza are of the same size. And if the pieces of pizza are of the same size, then when you start counting the pieces, it makes sense. Because 3 pieces here and 4 pieces here, making 7 pieces, it's not clear how much pizza that is. But when the pizzas are now sliced into the same size slices, it is exactly clear what 17 slices is. It's 17 slices of a pizza cut into 30. Make a common denominator, you're dealing with pizza slices of the same size, and pizza slices of the same size can be added one to the other. Anytime you're adding fractions, you need a common denominator in order to make the size of the pieces of your pie align. Alright, 2 more things and we will be finished for the day. So, first, how to refer to a portion of the number line. I'm going to give us 3 ways to refer to a portion of the number line. One way, graphical. Occasionally during the semester, we will make things graphical, make things pictorial, make things almost like a visualization. So we could look at a piece of the number line from, let's say, -1 to 2, and we could view it in a picture. I'm going to view it as a picture like so. It's sort of like a barbell from -1 to 2. I've got a closed circle at -1 and an open circle at 2. The closed circle means that I'm including -1. The open circle means that I'm avoiding 2. I draw the circle to avoid 2. I color in the -1 to show that -1 is included. Let's draw another example. This is a region of the number line between 1.5 and 4. Here we're going to include 1.5 and we're going to include 4. And in this last example, we're going to go from -3, not including -3, draw a circle around it to say that we're not including -3, but we are going to include everything to the right of that. All the way off to the right. So we're going to include -2, -1, we're going to include 0, 1, 2, 3, 4, 5, 6. In fact, 6.1, 6.11, 6.111. We're going to include pi, 2 pi, 3 pi. We're going to include all the numbers that lie to the right of -3. How else could we write this? Another perfectly valid notation to graphical is what we call interval notation. To make the interval notation, what we're going to do is we're going to grab the numbers that define the left and right endpoints of our portion of the number line. So for the first guy, we're going to grab -1 and 2, the left boundary and the right boundary, and we're going to separate those 2 values by a comma. Same below, 1.5 and 4, we're going to take those 2 values, separate them by a comma. -3 and, well, what's out here all the way to the right of -3? Well, you can't say that it's any number in particular, because we're going out off to the right as far as one could go. So what we could do is we could say that off to the right as far as one could go, in concept, would be infinity. Now, you can never actually get to infinity, but in concept, you're going all the way out to positive infinity. So when we grab the left boundary and the right boundary, it's going to be minus 3 and infinity. Now, how do we complete our interval notation? Because while we have included the numbers that define the boundary of our portion of the number line being considered, we have not taken into account whether or not the boundary is included or not. Whether the boundary is included or not. How could we denote that? Well, when a boundary is included, we're going to use a square bracket to include that boundary. On the left, we'll include with a square bracket on the left, and on the right, include with a square bracket on the right, if the right boundary is included, like 4 is included. Now, what about the boundaries that aren't included? We're going to use a parenthesis for that. So a parenthesis for the 2, because the 2 is not included. You can think the parenthesis is sort of like half a circle. It's like sort of like denoting a similar shape to the open circle, avoiding the number 2. Open circle at minus 3 as well. So we use a parenthesis to denote that minus 3 is not included. And then what about infinity? Is infinity included? Well, if you account for every number on the number line, do you account for infinity? No, you don't, right? Because you account for every number that's out there on the number line, but infinity is not on the number line. So infinity is merely the idea to represent the fact that we're going boundlessly off to the right into the positive numbers. So we don't include infinity, but we include everything up to it, which in particular is every number that lies to the right of minus 3. Okay, final way of thinking about numbers on the number line, we could use inequalities. This is really just taking the information that we have in the picture in the interval notation and articulating it in a different way. You could say that the portion of the number line that we talked about here is every number between minus 1 and 2, including minus 1 but not 2. To say that mathematically, we're going to say our number is every number between minus 1 and 2, including minus 1 but not including 2. Minus 1 is included, equal to, as well as x being greater than, and 2 is not included, x is going to be less than 2, but not including 2. What about the next interval? The next interval was between 1.5 and 4. Our numbers were between that, including both. It's just taking the left bound and the right bound and saying our number, x, is any number that's between 1.5 and 4, including 1.5 and including 4. What about here? We cannot include negative 3, and we cannot include infinity. But any number between minus 3 and infinity is included in our portion of the number line being considered. So x is between minus 3 and infinity. There we go. If you include a boundary, it shows up as a square bracket in interval notation. It shows up as greater than or less than or equal to with the inequality. If the value is not included, it shows up as a parenthesis or a strict greater than or equal to sign. All right, last piece for the day. Distance from 0. So what is distance from 0 going to address? Well, let's think about this. Imagine we're on a number line. You know where 0 is. Imagine we're somewhere off to the right, like at 5. Could you measure the distance from 0 here? You totally could, right? Because if you got out a ruler and measured the distance from 0, this would have a distance of 5. Get out your ruler and measure it. It starts at 0 and goes to 5. What if you were over here at minus 2? You could also measure this number's distance from 0. If you got out your ruler and measured this distance, this would have a distance of 2. Think about it. When you pull out a ruler and measure, there's no part of the ruler that measures into the negatives. So when we're talking about distance, getting out a ruler and measuring, the distance between these two numbers is positive 5, just like the distance between these two numbers is a positive 2. Take a number like negative 3.5. What's its distance from 0? its distance from 0 is 3.5, because you're 3.5 units away from 0. Now, when we talk about distance from 0, what is the mathematical word that we often use to associate with this? Distance from 0, we call absolute value. So if we want to talk about the absolute value of a number, we don't want to talk about the value being 3.5. We want to talk about the value being how far that number is away from 0. So, to denote absolute value, we use vertical bars. You've, I'm sure, seen this before. But just to be clear, if you talk about the absolute value of minus 3.5, the absolute value is the distance that minus 3.5 is from 0. If you measure the distance from minus 3.5 to 0, you get 3.5. Measure the distance from minus 2 to 0, put vertical bars on either side of a number. That means that you are asking someone or asking yourself, or whatever it may be, you're saying, vertical bars mean I am not considering what the number is. I'm considering what the distance from that number to 0 is. And the distance from minus 2 to 0 is 2. The distance from 5 to 0 is 5. In fact, the distance from any positive number to 0 is itself, and the distance from any negative number to 0 is just the positive version of that number. Distance from 0, the way that we often talk about this in math is to talk about this as absolute value, and the way that we denote it is vertical bars. Why? Frankly, I have no idea, but that's the way that we denote it. So as long as we know what we're talking about when we use vertical bars to denote absolute value being distance from 0, we're fine. In the same respect, as long as we know that a bracket means to include the boundary and a parenthesis means to not include the boundary, then we're fine. Maybe you prefer it to be the other way. If that's the case, I'm sorry. Like, the way that the notation works, in the sense, the way that we standardly refer to these things, is that a bracket is includes and a parenthesis is not includes. Just like the equal to would include and the not equal to wouldn't. Anytime you look at a portion of a number line, you can look at it graphically, visually, interval notation, inequality. All three columns say the same thing, just in a different way. You should be able to, given an interval, be able to cook up a graph and an inequality. Given a graph, cook up an interval and an inequality. Given an inequality, cook up an interval and a graph. That should be totally within your capacities after what we've talked about today. Okay, that'll be it for today. That rounds up what we had to discuss. There'll be a quiz here to finish off the class period. Remember, since it's now Thursday, homework will be posting on WebAssign due for, well, normally this Sunday we do, but since it's the first Sunday, we'll have it due next Sunday, sort of to get us rolling and give you guys time to get your WebAssign access code should you not have it. If you have a WebAssign access code, well then you've got an opportunity to start working on the homework as of tonight. We'll pick up tomorrow and grab ourselves a couple new things to talk about, and we'll just pick off from there. I thank you again for your attention. If you have questions, you can ask the sub. Otherwise, that's it for my time with you here through this video, and I'll see you guys tomorrow.